Welcome in. So we're going to talk a little bit about ionic compounds today. A little bit more complicated crystal structures because you got at least two ions, a cation and an anion. And they could get even more complex than that. Sometimes you've got mixed ionic compounds, so like two different cations with one anion or vice versa. So I'm already assuming that you're experts on those simple crystals, which is one element. And then also you're sort of familiar with the types of solids. We got the ionic versus molecular versus atomic. So we're jumping into ionic solids. And again, we're going to start with our favorite salt, sodium chloride. And we're going to try and pick out that simplest unit cell. And we're going to see coordination number. And we're going to try and count the atoms within the unit cell to sort of verify the chemical formula. So let me share my screen here. So here you see a picture of the sodium chloride unit cell, and they've already identified the atoms for us. The purple one is sodium. Cations are smaller than their neutral atoms, and chloride is the anion, it's larger. Anions are larger than their neutral version. And so, again, I'm going to jump into the Z diagrams here. And the way I think about the Z diagrams is, so you're looking at the crystal structure and you slice through, and you're going to slice through, sort of like horizontal, through every layer that has atoms. And when I'm looking at this, I see that there's three layers. I see all of these atoms are on one layer. So if I were to slice through that perfectly flat, I'd get all 9 of those atoms right through the middle of the nucleus. And then I see these 9 atoms, also sort of the second cut, and then these 3. So this set of Z diagrams will have 3 layers. And then what we might also notice is that the top layer and the bottom layer, what we would call Z equals 0 and Z equals 1, are identical. And we'll be able to show that over here. And then the numbering, the bottom is always 0, the top is always 1, and then the ones in between are sort of whatever makes sense to be equal. This one has only 1 cut between the top and the bottom, so it's half. If there were 2 cuts, it'd be 0.33 and 0.67. And we might see that on these other structures here. Another thing that we want to be able to pick up is coordination numbers. So if you look at that purple sodium in the very middle, the middle ends up being a great place to look for coordination number because all of its partners, all of the cation, all of the anions that it's touching or interacting with are shown. So I see 1 to the left, 1 to the right, 1 above, 1 below, 1 behind, and 1 in front. So this is octahedral, and we should sort of confirm that for the other ion. So the sodium is octahedral. It's very likely that the anion will also be octahedral. And I don't think there's one chloride here that's showing every single cation that is also shown. So we're just going to have to pick one. I'm going to steer clear of a corner because the corner, remember, is part of 8 different unit cells. And so if I pick one of the chlorides on a face, it's only part of 2 unit cells. And so if I pick this chloride here on that face, I'm going to label these with red. I can see that it's interacting with 1 sodium above, 1 below, 1 behind, 1 in front, 1 to the right, the middle one, and then the one that's sort of assumed and missing and not shown is to the left. So they're both octahedral. So sodium interacting with 6 chlorides. That means octahedral. And then the chloride is interacting with 6 sodiums. That's also octahedral. And now let's dive into the Z diagrams to count the sodiums and the chlorides. Obviously, we should get this ratio, 1 sodium to 1 chloride. But now we're seeing that salts and ionic compounds are more complicated than just 1 sodium and 1 chloride. You would have been forgiven if you walked in the door in Chem 1A, if you somehow thought that it was 1 cation and 1 anion interacting with each other and holding each other. But that doesn't really explain why table salt is these macroscopic crystals. And if you make it right, you can actually make these larger crystals too. And we see it's because you get this long range order in all dimensions. So this is the unit cell, and that means it repeats to the left, to the right, behind, in front, above, and below, over and over and over again, billions of times. So, even like the smallest little crystal might be sodium 1 times 10 to the ninth, a billion sodium ions, and a billion chloride ions, and then we just simplify it down. The simplest whole number ratio for ionic compounds is 1:1. So the unit cell should show that. So here, let's look at the Z diagrams. So we already said that the 0 and the 1 cut are the same. I'm going to try to color code it so we're all on the same page here. On 0 and 1, I've seen chlorides on the corners and in the middle. And I'm also seeing sodiums on edges. Okay. Actually, for this very first one, it might make sense to show all 3 cuts. So we'll do 0 down there, but then watch this. I'm going to do this. So the first cut is the bottom and the top look the same. And now the half cut, the middle, looks a little bit different because now we've got chlorides on the faces and sodiums on edges and in the middle. And so this is the hardest part about Z diagrams, is that the 0, the top and the bottom, where those atoms are, those are a little bit different than in the middle. So look, here, this top one, that is a corner. That is in 8 different unit cells. This, because it's in the middle, isn't a corner, it's a face. So the top and the bottom, where the atoms are on our Z diagrams, is different than the middle cuts. The same thing for the middle. This middle chloride here is on a face, but the middle here in the middle cut is actually in the middle. Okay, so we're going to treat them separate. So let's look at the bottom one. Here, for sodium, I have 4 on edges. 4 edges. And remember, an edge is 1/4 within the unit cell. And then the chlorides, I've got 4 on corners, and a corner is 1/8. So 4 times 1/8 is 1/2, plus 1 more right there on the face, plus 1 on one face. And a face is worth 1/2. So 1/2 plus 1/2, we got 1. So the bottom has 1 sodium, 1 chloride. We already said the top and the bottom are the same. So the top has 1 chloride and 1 sodium. Now we got to worry about the middle one. So the sodiums, I should have just done this in purple the whole way through. So the sodiums in the middle cut, I've got 4 edges. Sodium, 4 edge. Sodium, 4 edges. That's times 1/4 plus 1 middle. So 4 times 1/4 is 1 plus another 1. So that's 2. And then for the chloride, again on the middle, I see Yeah. 4 faces, and a face is worth 1/2. So times 1/2. 4 times 1/2 is 2. So the total atoms within the unit cell, now I add up all the Z diagrams. So total atoms in this unit cell. I've got sodium 1 from the top, 2 from the middle cut, and 1 sodium from the bottom. So 4. And then chlorides, 1 from the top, 1 from the bottom, 2 from the middle, 4. And again, that just simplifies to sodium 1, chlorine 1, and then again, the ones are usually omitted. Okay, so this unit cell shows that sodium chloride is 1-to-1. And it also shows that they're octahedral. This is called the sodium chloride unit cell. It's a very common unit cell if you've got an equal number of cations and anions. It doesn't really matter so much the charge. So for example, if you had like calcium oxide, technically that's +2 to -2, it might still adopt the sodium chloride unit cell because the ratio is 1-to-1. When you have different numbers of cations and anions, for example, like sodium sulfide, that's 2 sodiums to 1 sulfide, that might adopt a different type of unit cell. So we're going to get introduced to 2 more unit cells here. And before I go too far and draw a bunch of Z diagrams, this is actually a great opportunity for you to practice drawing some Z diagrams, count the individual atoms. We already know the chemical formula. We know that it's zinc 2 and sulfur is -2. So again, it's 1-to-1 ratio. The atoms within the unit cell need to reflect that ratio. This is a tricky one because the zincs are interacting with 4 sulfurs. So there's a tetrahedral arrangement here. And there's actually a couple different slices. I think everybody can see the top slice has those 5 sulfurs. There's a middle slice here that just has the zincs. Can you see all the angles? They're down to the zincs and then down again to the next sulfurs. And so then we've got our next slice here getting the 4 more sulfurs, another slice with just 2 zincs. And again, the angles are pointing in. They're not on faces. They're not on edges. They're what we call in the middle because the atom is completely within the unit cell. It's not like half in one unit cell and half in the other, but you might notice that it's not technically the middle. The very middle of this unit cell doesn't really have an atom. And then you got your bottom cut. So you got your bottom, you got your top, you got your middle, and you got the 2 cuts with the zinc. So we got to show 5 different layers here. So try to show your 5 different layers. Try and count the atoms. Looking at, again, there's 4 places atoms might be. Corners for 1/8, faces for 1/2, edges for 1/4, and middle for a whole. And let's see what you get. So pause the video, come back, draw, see how close you got, and then we'll go from there. So we already said that the top and the bottom are going to be the same. I might do the same thing one more time here. So the 0 cut is the bottom. It's got those 5 sulfurs here. It's a little too light. Can you see that? I hope you can see that. And again, since it's the bottom cut, those corners are true corners in the unit cell, and the middle is actually a face. So these zincs, I might do them as we go here. The zinc is 4 times 1/8 plus 1 in on the face, so times 1/2. 1/2 plus 1/2, 1 zinc atom is within this unit cell. So then you got 5 cuts, 0.2, 0.4, 0.6, 0.33, 0.67. So I think the one with zinc ions here is 0.25, the middle is 0.5, and then this other zinc one is 0.75, and then the top is 1. So then we'll have a zinc, Z of 0.25, and this one has some zinc atoms, and they actually look like this. They're totally within the middle. Oh, sorry, I messed up on the bottom. It wasn't zinc, it was sulfur, sulfides. These are the zincs. And now I just got 2 in the middle. So 2 zincs. So far I'm up to 1 sulfur, 2 zincs. Now we'll go to the half layer. That's in the middle. We got those 4 sulfurs. All of those are on faces. 4 times a half. So you got two more sulfurs. Then we'll go up to Z equals 0.75. Notice that these zincs are a little bit off from the other ones. I had top left, bottom right for 0.25, but for 0.75, I got top right, bottom left. I'm sort of looking down when I draw my Z diagrams. So there's the two zincs. And so same thing, we got 2 in the middle. So that's 2 more zincs. And then Z equals 1, again, I could just sort of steal the bottom, everything from the bottom. And so now when we count all of the atoms that we have here, I had 4 zincs from 0.25 and 0.75, and sulfurs, 1 from the top, 1 from the bottom, and 2 from the middle. So this one also ended up being 4 of each, which again simplifies down to 1. The empirical formula is just 1 zinc, 1 sulfur. That's called a zinc blend structure. Again, it's got this tetrahedral geometry, and the book pulls out that tetrahedron. We got one more unit cell we'll talk about here. And again, the things that we're practicing, I guess we could talk about coordination number. They're pretty explicit with coordination number. 1, 2, 3, 4 for the zincs. What about for the sulfurs? We don't have a sulfur in the middle, but we got a bunch that are on faces. And so we see that this, I'm looking at this sulfur right here. It's got 1 coordination to a zinc there, 1 to a zinc there. We would assume that in the unit cell next to it, it has 2 more for a coordination of 4. So calcium fluoride, here's finally a structure where we don't have 1-to-1. We need to have double the fluorides. Again, pay attention to ions. Pause the video here. Try to draw your Z diagrams. Try to tell me how many total atoms of calcium are within the unit cell, how many total atoms of fluoride are in the unit cell. Did that verify the calcium fluoride units chemical formula? So we got our bottom slice again. That's going to have those 5 calciums. I see another middle slice, but this time it's 4 fluorides, all within the unit cell. I see another middle slice getting 4 more calciums. Another middle for the 4 more fluorides. So that one and the bottom one actually are identical. Those 8 fluorides are sort of on top of each other. And then the top looks just like the bottom. So this looks similar as the last one. You got 3 middles, so call them 0.25, 0.5, 0.75. And a couple of them are repeating. 0 and 1 are the same, and 0.25 and 0.75 are the same. So on Z equals 0, we've got some calciums. And calcium 4 times an eighth plus 1 on the face is a half. So that's 1 whole calcium for the bottom cut. Again, that's within the unit cell. And then Z equals 0.25. The angles here are showing us the fluorides aren't on a face or an edge or a corner. They're totally within the unit cell. So here we're showing 4 fluorides. Don't show them on an edge. Don't put them like around on the black line. They're wholly within the middle. And so this is fluoride. This is 4 middles, and each middle is worth 1 whole one. So that's 4. And again, the 0.751 is the same. And now the half one, that one's a little bit different than the top and the bottom because we've got them here. If that was happening on the top or the bottom, it would be an edge, but because it's in the middle, they're actually on faces. Sorry, I meant to do that in dark blue. So that's going back to calcium. That's 4 on that slice, and they're half within the unit cell. So you got 2 here. So now when you look at the total formula, the total number of atoms inside this unit cell, I've got 1 calcium from the top, 1 from the bottom, and 2 from that 0.5 slice. So that's 4. And then fluorides, all 8 of them are totally within the unit cell. So that's 8. And then that simplifies down to 1 calcium to 2 fluorides. One thing that we'll see here, it should be pretty easy to see the coordination number, especially for the fluorines in the middle. So the fluorine, 1, 2, 3, 4. So again, we're seeing that coordination number of 4 for fluorine. So the coordination number is 4. But what about the calcium? Calcium is actually quite a bit different, and this has to do with maybe well, I guess I won't say anything about that. I was going to say something about size, but they're showing them actually very similar in size. Fluoride minus should be a little bit bigger, but it's second row. Calcium cation should be a little bit smaller, but that's third row. And so I think that they're actually very similar in size. So let's pick this. Can you see that? I'm showing one in light green there. A little bit darker green. Let's look at that 1 calcium. It's on a face, so whatever we find for its coordination number, we'll double it into the other unit cell, the unit cell to the left. And so I'm seeing it interact with all 4 fluorides that are next to it. So we would assume that it would interact with all 4 fluorides behind it. So the calciums actually have a coordination number of 8. I've got more down here, but I was planning on doing it, but I feel like after we did those last 3, you're probably feeling pretty good on it. So try these other 2. These again from your textbook. I think they're even problems in the book. If you have any questions, feel free to ask. Lithium oxide, we know that lithium forms a +1 and oxygen forms a -2. So we need to get that Li2O formula. And so use the Z diagrams, use corners, edges, faces, and middles to count the ions. In silver iodide, silver always makes the +1, iodide always makes the -1. So that's going to come together to be 1 to 1. That actually looks very similar to one of the 3 that we already looked at. So that's just a quick introduction to some unit cells for ionic compounds. You could spend probably the rest of your career looking at unit cells and crystal structures for ionic compounds. There's some really interesting ceramics that have 4, 5, 6 different metals and non-metals, and they try to make perfect crystals with interesting maybe structural or electronic properties. A lot of like superconductors are ionic compounds and perfect crystals. And so they would be doing this work. This is something that you could, make a pretty good career out of. But this is, again, just sort of the intro to it. So I hope you feel a little bit more comfortable looking at a unit cell for an ionic compound and trying to figure out what the chemical formula is, trying to verify that chemical formula from that unit cell. It always comes down to trying to break down the problem in the way I've shown it, one layer at a time. When you just step back here, there's a lot of atoms here. There's like 23 atoms. And so to try to digest it whole is a lot, especially when you factor in that this one unit cell is interacting with something like 26 other unit cells, 9 above, 9 below when you factor in corners, and then 8 around it. So it can get pretty big and cumbersome pretty quickly, but again, focus on one thing at a time. So we looked at this one atom and we said, okay, it's on a corner. It's an 8th in there. And then there was 2, 3, 4. So that meant there was half the calcium atoms within this one unit cell. And then we said there's one more on a face. That's worth another half. Therefore, this whole Z slice was worth 1. Break it down one step at a time.